So we can see when x is minus pi, f is going to be 0, right? So it goes from 0 to, let's say this is 2 pi height, 0 to 2 pi. Yeah? And at the point pi it is not defined. Yes. So again it will go on record like this. Okay. So it will do that. So that's your function. Now of course what we can do is we can directly find the Fourier series, but that's very clumsy. What we are going to do is to see f of x can be written as f1 plus f2, right? Where f1 of x is x, yes, and f2 of x is pi. So basically f2 is a constant function pi, yes, and for a constant function the Fourier series is going to be a naught is pi and then everything else we don't have, right? Okay, so what we are going to do is essentially, first of all, let's just find out this thing for the function f1. What is the Fourier series, right? Okay, so uh, see f1 of x is x, so f1 is an odd function. See, since f1 is odd, ans are going to be 0 for all n equals to 1, 2. So you remember, right? See which one is among sine and cosine, which one is odd? Sine is odd, right? So essentially this the Fourier series which you are going to get is in terms of sine, right? So the cosine part, the an part, they are going to be 0. And what about the bn part? Bn's are nothing but, so in this case, see, it will be 2 by pi 0 to pi, right? f1 of x sine nx dx. I hope you understood why it is 2 pi. See, b is generally 1 by pi, but the thing is that is from minus pi to pi integral. But since this is a odd function, we can just do it between 0 to pi and then that 2 extra is coming, you see. You remember? See here, one second. I did not write it. Yeah, I did not write it. Oh yeah, I did it. You see, if you have a even function minus pi to pi g of x dx is 2, 0 to pi g of x dx, right? If it's an even function, so it becomes 2 times 0 to pi. Yes. So here also you do realize that if one is odd and this is odd, so the multiplication is going to be even. So this whole function is even. So you can just write it to be 2 times 0 to pi. Okay. Now I want you to check this part. Please check this. Yes, check it. That if you integrate this thing, it becomes 2 by pi, then 0 to pi, and then you have x sine nx dx. Yes, so it becomes, if you calculate it, it becomes 2 by pi cosine n pi. Yeah, so you have to check this part. Yeah, please do this check. So maybe you can check this. Let me put it here. Check. Okay, right. So if you, therefore what happens to b1? b1 is going to be 2. See, n equals to 1, 2, right? And b2 is going to be minus 1, right? See, it is minus 2 by pi, yeah, and then cosine 2 pi. Yeah? So b2 is going to be, one second, what am I doing? 2 by pi, sorry, it should be 2 by n, that's a small mistake which I did, because this is does not depend. Yeah, it becomes 2 by n, sorry about it. Yeah, that's what. Okay, so b2 in this case becomes minus 1. So it is, see, n equals to 2, so it is minus 1, and cosine 2 pi is 1. So that is why this b2 is minus 1. Again b3, if you can calculate it, cosine 3 pi minus 1, and then minus 2 by 3. So it is 2 by 3. Yeah, minus 2 by 3 times minus 1 is 2 by 3. then before you can of course calculate it, it becomes minus 2 by 4, which is half. Okay, and so on so forth. Yes. Now what happens to f2? Again, you see f2 is a constant. So what is the Fourier series of f2? f2 of x Fourier series is essentially you have a naught, that's constant thing, which is pi. So that this is your a naught in this case, right? And what about ans and bns? They are always going to be 0. If you are not convinced, you can check. You see, it becomes pi times sine nx or cosine nx, which is definitely going to be 0 over minus pi and pi. So that part is there, right? So the Fourier series of a constant function is the first term, I mean it itself basically. So what is the basic, what is the Fourier series of f of x then? Therefore, the Fourier series of f of x is, so first of all we will define this pi, we will add this pi with the Fourier series of f1, 2 times sin x plus, sorry, minus, this minus is there, so minus half times sin 2x. Okay, so minus 2 and 2 is getting cancelled, so minus sin 2x, that's what we are writing it like this, yeah, plus 1 by 3, so that it looks nice, that's all basically. You see, 2 by 3, this is 2 by 3, 2 by 3 sin 3x, minus this is 2 by 4, right? So minus 1 by 4 sin 4x, and you can go on doing this thing. Is it okay? So that is your I mean how to work out this sine or cosine series and how to use it to find problems like this. Is it okay? So basically for functions like this, which is in terms of sums or products, what you can do is you can find individual Fourier series and then write it in this way. Yeah, and of course you can take up an example like this. You see, let's say this, so note or a small remark, maybe I can put it as a remark. Let me put it this way. So a small remark, let's say the same problem, do this thing. See, 2x plus pi. See, first thing first, the Fourier series of pi, which is going to be pi, nothing changes, right? So let's say this is your f1 and this is your f2. f2 is pi. f2 is pi. So f2 pi, the Fourier series is going to be pi, no chances. Now what is the Fourier series of f1? See, you remember c times f is c times the Fourier coefficient of f. So you find out the Fourier coefficient of f. So in this case, what is the Fourier coefficient of? So you see, you can write it as c times f1, right? So where c is 2. Okay, f1 of x is x. Now for f1 of x, you know what are the Fourier coefficients? You see, the Fourier coefficients are 2 minus 1. So basically, what you do, you multiply it by 2 and then you write down the Fourier series. Yeah. So I hope you understood what's happening here. So you have to, again, you try and solve this. Yeah, very easy. So again, do it yourself. Yeah. Okay. So I hope this is very, easy, right? It's not an issue here. So now what we are going to do is going to look at something called a half range expansion. Yeah, this is very, very important. Half range expansion. So what is an half range expansion? Let's just understand that. So essentially, let's say that, you see, it may happen that your function, see, let us do it here. See, the function may be defined here in AB. Yeah, defined on closed AB. Let's just assume this. Now if it is defined on closed AB, what happens is you can just shift this function, right? You can just shift it to 0 and some L. Is it okay? 0 L, of course. You can take the whole thing and shift it to A, the base to A. So basically A minus A becomes 0 and then B will be B minus A. That's all. Okay. So for example, let's say 2, 4. The function is defined in 2, 4. Now you define another function by just changing the the interval from 2, 4 to 0 2. Okay, so do it like this. Okay, so I mean there will be one problem which will be in the assignment also, how to shift this thing. Yes. And this is very simple, right? So please do it yourself. So this part you have to check. Now let's say that now you have this change, and now you have f is defined in 0L. Yes, defined on 0L for some L. For some L can be positive, it can be negative, doesn't matter. I mean, basically for 0L, this is assume for now. Yes. Okay. For now, L is positive. Yeah. See it. I mean, of course, you can shift. I mean, F, right? You can translate it. And so basically, once you do it, you can of course get it like this. So, okay. Now, what do we do now? So let's say you have a function which is defined on 0 and L. Now, the aim is this. Aim is to find the Fourier series of f. How do we do it? Fourier series of f. Series of f. Okay. How do we do something like this? So what do you think we should do? See, what happens is this. There are two ways of looking at it. Okay. So let me do it here. And this is, I think, drawing this stuff is important. So let's say you have a function, yeah, defined on 0L. So initially we start with f which is defined between 0L to R. Okay, and of course is 2 pi periodic, okay. Sorry, 2L periodic. Okay, so for now let's just assume that this is 0L. We don't have to work about periodicity, it's just defined on 0L, and we want to find the Fourier series here. So what to do here? So let's say 0 to L, and the function looks like this. Okay, maybe the drawing, maybe I can draw it like this. The function looks like this. Okay, now what happens is this. How do we put the Fourier series in action? See, we know how to work for this sort of function. Let's say how to do the Fourier series of function from minus L to L. Right? For this sort of function, we know how to do work with the Fourier series. Okay, so what to do here? The function is only defined between 0 to L. So what we do is this. First of all, we do something called a even extension. So maybe I can write it here. We first of all start with an even extension. So what is an even extension here? Even extension, if you think about it, what happens is this. You are just extending the function. The function is defined between 0 and L, right? And it looks something like this. Yeah, my drawing is not very good, but you do realize what's happening here. So we are thinking of this same thing. We are taking the image in the other way. So basically, if you put a mirror in this y-axis, think of it like this. You are just looking at the reflection of this particular graph on the other side. Okay, so essentially that's your even extension. So essentially, what am I doing? I am defining a new function. So define g of x. Yeah, this is my new function g of x. And how am I defining it? I am defining it using this. See, this is f of x if x is between 0 and L. Okay, let me write it like this. So for x in 0 and L, see, our new function g is essentially f between 0 and L, and this g we want to define. So we want to define it between minus L to L, right? So what you see here also, it is doing the exact same thing. Yeah, and so for x between minus L to 0, this should be okay. First of all, let's see the functional value does not change, right? So basically f of, okay, let's take an example. Let me tell you what is happening. Let's say L is equals to 1, L equals to pi, let's just assume that. Okay, and at the point 1 it is taking the value. So at the point 1, let's just assume that it is taking the value 2. Yeah, some example, doesn't matter. Okay, so at the point 1 it is taking the value 2. Yeah, so I want the same 2 value at the point -1. So when x equals to -1, I want f of x to be 2. Yeah, so if I have to do something like this, I have to define it using f, right? So if I am defining this as f of minus x, then you see what happens is f of minus x is f of minus x is f of 1, which is 2. So it's basically an even extension. You understand what's happening? So that's the idea. Okay, I hope this is clear what is happening here. See, again, let me again explain to you what's happening here. Okay, let's say that I have this function initially between 0 and L. This is the function. Okay, now what I am doing is this. I am extending the function to minus L and L because I know how to find out the Fourier series for minus L to L. Yeah, and you see how am I extending it? Let's say there is a point x here. Yeah, and at that point, what is the functional value? F of x. It is f of x, right? This is the height. The f of x is this, the height. Yeah, okay. So you see what I am doing is this. At the point x, the functional value is f of x. Okay, what do I want? I want the exact same thing to work here also. See, the functional value should also be, the function should look exactly like the same. My drawing is extremely bad. I'm sorry about this. Okay, maybe I can. Okay, something like this. Yeah. So we want, you understand, right? It's symmetric. Basically the same thing here. So at the point minus x, you see, at the point minus x, we want the functional value to be f of x. So we want it to be f of x. We want g of minus x to be f of x. You understand? So basically g of x has to be f of minus x, right? Okay, so in this way, now if that happens, now you do realize that this new function g, what sort of, so check that g is an even function. Actually there is nothing to check. This is basically the definition of g. I mean even function, but I mean you do but please anyways, I mean if you are confused or something, you can do that. So g is an even function. Yes, and now you have a even function and you have so you have a new even function defined where? Defined on minus L to L, right? Minus L to L. And for this even function defined on minus L to L, you know what is the Fourier series. Yes, and then you write down the Fourier series. Yes, once you write down the Fourier series, what you do is you basically restrict it to 0 and L and you are done. I hope this is clear to you. Okay, what I am going to do is explain you the exact same thing but with an example. Okay, so you understand what's happening, how to work out. Yeah? Okay, so this is even. Okay, let me do the odd one also and then I will give you an example so you'll understand what's happening. So now let's do the odd extension. See this extension, what I am doing. So basically our idea is we want to write the function in terms of not 0L but minus LL, right? And this even extension is there. So this is even extension. Okay, what about odd extension? So let's say our function between 0 and L is given like this. I'm drawing it like this because that will make my life easier. That's all. Nothing special is happening here. So, but I mean, maybe I can draw it like this. Yeah, maybe I can draw it like this. So same value here, and maybe I can draw it like this. Yeah. So let's say this is my function given. Yeah, and f is given here between 0 and L. Yeah. This is my function given. Now what I want to do is I want to write it between minus L to L. Yeah. Of course, I can do the even extension. If I do the even extension, you do realize that I have to do something like this. Yeah, basically the reflection of this with respect to the y-axis. Now, what we are doing here is we are doing similar sort of thing, but in the negative axis. So essentially, we have similar thing, but here. Is it okay? Fine. Yeah. So what happens is, in odd extension, we define the odd function. Define g of x, which is f of x, of course f of x 0 to L. So essentially we have the same function in between 0 and L. Okay, what happens if x is here? So let's say if I am taking x from here, yeah, I want the exact same. So at the point minus x, I want my g, yeah, to take the functional value f of x, but minus f of x in the negative axis, right? Okay, so what I want g of minus x to take the functional value f of x only. You see, I want to take f of x functional value, but in the negative axis, in the down, right? So I want f of minus f of x. Okay, so basically g of x, think of it like this, minus f of minus x. This is what we want. So this is minus f of minus x, and x is between this is 0 L, right? So it has to be 1 second, 0 L, oh sorry, minus L 0. I hope this is clear. Now of course you can check that this is going to be odd function. This is just a definition. Now for an odd function, you know that you can write the Fourier series, yeah, you remember? So for an odd function, if you write the Fourier series, it will be Fourier sine series. So only the Bn terms will be there. Okay, right? So and then you just calculate it and just restrict the function to 0 and L. You should, because once you restrict, see, you get the Fourier series between minus L to L. Now you could just restrict it to 0 to L. That will be the Fourier series of f on 0 to L, because the extension function is basically the Fourier series in the whole minus L. Now you are just restricting it to 0 to L. That will be your f. So that's your Fourier series. Okay, without talking much, let us just write it down what exactly it means. So let me give you an example, right? Okay, so an example of this extension. Yes, I will do one example, and then I will, of course, I am not going to calculate the whole thing. I will just explain what is happening here. Okay, so let's say f of x, and for now I am not taking minus pi to pi thing. Let's just do it between sorry, I am going to take pi to pi, so minus pi to pi, L equals to pi essentially. Yes, okay. So in this case, if I am taking L equals to pi, what I am going to do is my new function here, the function which I am going to talk about, is 2 pi times x. Is it okay? This is what we are just, this is just a basic function which I'm just writing it like this, clear? And this is between 0, x and pi by 2. Let's just put it this way. Yeah, I'm just defining a function, don't worry about it. It's nothing special happening here. And then 2 by pi, let's do it like in our case it is pi minus x. Okay, so this is between pi by 2 and x between pi. We'll do it like this. Is it okay? So essentially a constant times x in 0 to pi. Yeah, so it will do something like this. See, 0 to pi by 2. So it will be some function, 2 by pi, some constant times x, essentially something like this. And then at the point pi by 2, you see, at the point pi by 2, this becomes pi by 2. So this gets to be 1. Again at the point pi by 2, this is 1. So essentially it will be similar sort of thing. At the point pi, this is 0. So it will become like this. You see, this triangle kind of function. You understand? This is just an example, but a very special example. This is a triangle function. You can think of it like this. The function is defined between 0 and pi. Of course, what we will do is we extend it to minus pi and pi, minus pi to pi. That is how we are going to talk about Fourier series. Okay, so first of all, we can do an even periodic extension. So let's do an even periodic extension. Now you do realize that it doesn't really matter if you do an even periodic extension or an odd periodic extension. Yeah, both are valid. It's not of course you are not going to get the exact same series, because one will be in terms of cosine, one will be in terms of sine, but the thing is both the series is going to represent f. Yeah, because this function f is here, it is a very nice function, right? It's a continuous function, and basically differentiable everywhere except at a point, so it's absolutely no issue here. Okay, so let's look at even periodic extension. What we do, First of all, let's just find out. So you understand even, right? So cosine is even. So basically the series which I'm going to get it in terms of is cosine. Yeah. So the bns will be 0. The sine thing is 0. So a naught is 1 by pi. Okay. And then 2 pi 0 to pi by 2. Okay. And then x dx. So basically 2 by pi x dx, I am just writing it like this, plus 2 by pi, pi by 2 to pi, and then pi minus x times dx. Is it okay? Yeah, we can write it like this. Now I'm not calculating this thing, but you can of course calculate it. It's going to be half. Yeah. Now don't be 100% sure on my calculations. It may happen that this is wrong, so please check. Yeah, but essentially this is basic integration, right? You can of course handle this part, so please do that. Okay, what about ans now? What about bns? Bns are going to be 0, right? Bns are going to be 0 because this is basically a even extension, so it's a cosine series. Yes. What about ans? So this is going to be 2 by pi. You remember, for even extension it is 2 by pi, and then the integral is not between minus L to L, it is between 0 to L. Yeah, so we don't have to, even though we are doing the even extension, the integral is always between 0 and L only. Okay, so it becomes, I hope you understand what's happening. See, I mean the function f, we are doing an even extension. Yeah, so g, like this even extension, whatever we did. Yeah, we'll define it like this. Now for that g, this is a Fourier series. Yeah, this is a even function, and the Fourier series will only contain the cosine series, the cosine terms. Yeah. So if you remember, the a naught is 1 by pi 0 to pi fx dx, right? And what are ans? If you remember, ans will be 2 by pi. Yeah, because 2 times pi, this is 0 to pi. Remember, it used to be minus pi to pi, but then since it is even, so we are getting 2 multiplied here, and then it is f of x dx. Yes. So in this case, you see, in this case what happens is 0 to pi, it will be g of x dx, the extended function. But in 0 to pi, what is happening, the extended function is basically the original function, right? So it is f of x dx. You understand? So although we are doing an extension, it does not really matter. Yeah, because we are essentially doing the integral on the whatever the initial problem was. Okay, so now what we do is we write it like this: 2 by pi 0 to pi by 2, right? One second, this should be pi by 2 to, one second, where should we do it? This is 2 to pi. Yeah, it's fine. Yeah, sorry, this is 2 to pi, 0 to pi, 0 to pi by 2, 0 to pi by 2, and then f of x is x dx. Yeah, sorry about it for the little confusion. And then again, again 2 by pi, 2 by pi part is there, 2 by pi, and then pi by 2 to pi, and then pi minus x. Okay, I have missed a cosine here. I'm really sorry about this confusion. This is a cosine nx dx. Yeah, this is ans, right? So this is f of x cosine nx plus 2 by pi, pi by 2, 2 pi, and then it is pi minus x cosine nx dx. Yeah, because we have split 0 to pi interval between 0 to pi by 2 and pi by 2 to pi, so we can write it like this. Yes. Now again, this is some simple integration theory essentially, but of course I mean this is for you to figure out what's happening here. Okay, so what I will do is, so please check, this is for checking, you have to check it yourself. Essentially what happens is, I will just write down what the ans are. In this case, ans are 4 by n square pi square, okay, and then 2 cosine n pi by 2 minus cosine n pi minus 1. Okay, so essentially you see I did not calculate the whole thing. What I will do is this, here essentially I want you to please check this part. Yeah, please check this yourself, what is going to be the ans. Yes, this is basically integration, but that part you can handle yourself. So essentially what is f of x in this case, what is the Fourier series? See, f of x in this case will be a naught is half, so it is 1 second, half, yes, and then you have a terms, right, minus, see, n equals to 1 is 4 by pi square, yeah, an cosine n x, right, so a1 cosine x, this is a big calculation, yes, so n equals to 1 is cosine pi by 2 minus cosine pi, okay, so it will be, let me do it this way, so maybe I can write it like this, 16 by pi square and then 1 by 2 square cosine 2x, okay, plus 1 by 6 square cosine 6x, plus it goes on like this. Yeah, it's just a big calculation. N equals to 1, n equals to 2, you have to put it together and write it like this, but essentially this is the fact. So this part you have to check. Yeah, please do check. See, one good thing about checking is you will get a very good idea of what exactly is happening, right, and you will get confidence of how to do it. So that's your even periodic extension. The basic important part is this, you understand. So essentially what happens is the function is defined between 0 and pi. Clear? What we are doing is we are taking an extension. What we are doing is we are defining a new function g, which is an even function, which is defined by this. You see, g is defined by this, yes, and this g is defined in minus pi to pi. Clear? Now for this g, see, by definition g is going to be even function, so essentially the series which you are going to get is the cosine series. Bn's are going to be 0. Okay, a naught, of course you can check, a naught is going to be half, no problem here. What about an's? You do realize that an's will be in this case 2 by pi 0 to pi g of x dx, right? I will explain, I am explaining again. See, g is our extended function which is defined between minus pi to pi, but essentially the Fourier coefficients of g does not depend on minus pi to pi, what g does at minus pi to pi. It depends on what g does between 0 and pi. Okay, what does g does at 0 and, you see, L is pi here, so what does g does at 0 and pi? It is basically f, so it is essentially 2 by pi 0 to pi f of x dx. Now you see, if you already know what happens at 0 to pi, so you just put that integral down and do it. It's just calculation, nothing special. This is the important part. Again, let me show you what happens in an odd periodic extension. Similar thing, odd periodic extension. The calculation part I am not doing. You guys are better in calculation than me, absolutely. So you please do it yourself. What I am going to do here is this. See, you can check that bn's are going to be, so in this case if you are doing odd extension, we'll do it like this, odd extension, yes, and the function g which you are going to get is an odd function, and the Fourier coefficient, if you remember, bn's are going to be 2 by pi, yeah, and then 0 to pi, yeah. You remember it will be minus pi to pi, but the 1 by pi minus pi to pi, but the thing is minus pi to pi, it gets converted to 2 times 0 to pi, yeah. So 0 to pi, and then you have f of x sin n x dx. Okay, and you know what f is at 0 to pi, which is given like this, yes. So you just put it there, and for now again I am cheating a little bit. I will just write down the answer for you. It is 8 square by pi square. Okay, and then sine n pi by 2. Is it okay? And then f of x, which you are going to get, is going to be, let me write it this way, it will be 8 by pi square 1 by 1 square. Let me write it this way, yeah, it will be better. Sine x minus 1 by 3 square sine 3x plus 1 by 5 square sine 5x minus, it goes on like this. Is it okay? So you have another function, yeah. So you see this f and that f is different. You see the Fourier representations are different, but the thing is, if you put a particular value, this is a continuous function with a nice and derivative thing, right? Only one part there is a problem, but the left and right derivative exist in this case, so absolutely no issues here. So essentially what I'm trying to say is this sum, this is a different series, but the thing is this series converges and the sum is going to be f of x. And similarly in this case, the series, this series converges and the sum is going to be again f of x, yeah. So both these series, the sine and the cosine series, actually determines the exact same function, yes, and the Fourier series of the same function, but they just look in terms of sine or cosine. So this is your extension in terms of odd and even. I hope you understood it. So with this, I'm going to end this lecture.